An instance can have 0, 1, or many nodes, so you can have as many as you want. The key thing is that the backing implementation is the CB-ops entry point. So CB-ops is the character and block operations that a driver implements. So this would be the read, write, open, close. Typically you need open and close, and almost everything else after that is optional. Read, write, strategy, IOCTL. There's one called dump. Can't remember what other ones there are off the top of my head. And typically these you call DDI create minor node, DDI just destroy minor node, and your attach and detach entry points. So, if you've got an example, remember we had, here's another example of how do I create a driver. Well, first I got to put the kernel module in the right place, and as 9 times out of 10 you're probably going to be stashing it in kernel in this directory. If you're a driver developer. There are other places, and I'll mention those briefly in a minute. And then you'll use this add drv command to create it. You notice -i, comma, -i, single quote, close, double quote. The ordering there is important. And I can list, I could have listed multiple aliases. For the sake of brevity here, I only listed one. And then the actual name of the driver itself. And this registers the device with the system, and it'll cause the entry point, or the aliases to get put into that file, etc driver aliases, and now the system will be able to access this thing. If you have hardware present, it will also automatically attach the driver for you, unless you can specify a flag requesting to defer that until the next reboot. Normally, you only want to use adddirv once. And then, while you're testing new drivers, it's better if you can mod unload and mod load your new driver. There are some special cases where that's difficult to do with things like HBAs. And there's some sneaky tricks you can use to get around that. I haven't talked about all this. It's, again, limited amount of time. So what happens when I have a new driver? A init is going to get called as the first time the ELF module loads in the system. And you'll use this to initialize your globals, and it's register what type of driver you are and the rest of your entry points. So actually what's interesting here is that init, there's two things. A well-designed driver should actually only have 2 external symbols. One is init and the other is fini. Everything else is basically registered in the system as through these structures, which can actually be defined locally. And that means that if you have your driver is all in one source file, all in one translation unit, you can actually get really good optimization because everything's static, right? The only thing that needs to be global is init and fini. Anyway, once the ELF module is loaded, if you have an instance, the configuration is going to call attach for each instance that it finds a matching alias for, right? So, and we'll look at some specific example code in a bit, assuming that there's time. That's a big assumption. The opposite of this is detach and fini. So, what's interesting is that normally you don't see detach get called unless you're using, I didn't talk about these tools like config-adm. You can manually detach one device. But typically, the way you're most likely to see it detach is in the process of trying to unload your ELF module. When you're trying to unload the ELF module, what's going to happen is fini is going to get called, and then fini will try to do a mod uninstall, which will then cause the detach for each instance to get called. This is really important. If your device is busy, you want to refuse the detach, so you would return DDI failure, and the system will fail at attach time, there'll actually be an error. No, I probably think it's ebusy that mod uninstall gets back, and that you return back through fini. Ultimately, that causes mod unload to fail. So your module, it would be really bad if your text module got unloaded while you were still using it. When you're doing kernel programming in illumos, one of the things you need to be aware of is context. This actually shows up in man pages for interfaces. There will be a document that says, context. What context is this function available in or safe to use in? So user context is the most generous. Every function can be called from user context. This is, you're running on a normal thread, and the thread has a user process associated with it, meaning it has a user address space. The only functions I know of that require user context but won't work in a kernel context would be the copy in and copy out functions, because those you need an actual user address space to get to. For everything else, almost every other time you're going to find that you're in kernel context. Kernel context is a normal, regular priority thread. And actually, it's a regular thread. It'll be running. I didn't talk about threading priorities at all, but it's just a thread, and you can block, you can sleep, and so forth. And so for most kernel programming, you don't really have to worry about oh, I have this subset of functions I can call, because most of the time you'll find that you're in kernel context. The exception is when you're in interrupt context. Your interrupt service routine, these actually run on a thread, but it's a special thread, and there's it's generally considered poor form to block, and you have to initialize the mutexes that you use for synchronization with a cookie that basically prevents other threads of equal or lesser priority from running at the same time. And then there's high-level interrupt context, which doesn't run on a regular thread, and you really should not be using it very much. High-level interrupt context means that you're operating at what we call above lock level, and it should only be used for particular classes of device where you have extremely tight latency constraints. So the canonical example of this was a serial port where you have a very small FIFO, and you can't afford not to. If you don't service it quickly enough, you can lose characters on the FIFO. And typically the strategy for running a high-level interrupt context is to do a tiny bit of work and post just to service the device, and then defer a bunch of stuff to what we call a software interrupt that runs as a normal interrupt. So you wind up with a two-level strategy for interrupt handling. It's a pain in the neck. The only time I know of where high-level interrupt context comes up frequently is if you're working on the clock code or you're working in serial ports. I can't think of anything else that needs it. The nice thing is for PCI devices, you can select the interrupt. There's ways to force the interrupt priority if you. For synchronization, remember I talked about everything's a thread. So mutex enter, exit, we have read-write locks. There's condition variables. You'll notice I didn't put semaphores on here. We do have semaphores. The block framework uses semaphores. I don't like semaphores because semaphores suffer from a problem relating to priority inversion. There's no owner. So most of the time I would prefer to see a mutex rather than a semaphore. Likewise with read-write locks. The nice thing is these things, if you've programmed with POSIX threads, you're going to find that these things pretty much map to the POSIX primitives pretty closely. In fact, they map real closely to the Solaris threads, userland threads API, if you remember the old Solaris userland threads API. So there's a lot of, it's very easy to understand. If you've only worked in Linux kernel or something like that, this might be a bit foreign to you. A big thing that we see driver developers needing to do a lot is work asynchronously. So we have actually, remember I said everything's a thread, and there are ways to create a thread and manage it, but those use private interfaces. So we have a public interface, which is our task queues. Task queues is the way you should be running. If you need to run something asynchronously, 9 times out of 10, you should probably be using a task queue. If you find that you need to do things periodically, periodic housekeeping and stuff, there's a VDI periodic function, and that's nice. And the nice thing about that is that you can specify an interrupt lock, a lock level with that from an interrupt cookie. so that it can work. It can block at the same. You could share data between the interrupt service routine and your periodic, which is pretty cool. If you just have a single timer, use timeout. There used to be an old pattern before the periodic interfaces got added, where you would call timeout, and then you would reschedule from inside the timeout. And there were a lot of bugs and buggy drivers around this, what happens when you unload the driver, because there's races associated with unregistering the timeout. So the periodic stuff is better. I talked about the soft interrupt. The only time I think you need soft interrupts is when you're doing that 2-level interrupt processing, because you're dealing with a high-level interrupt. And actually the only time I've ever, in my entire career, had to touch this was working in the PCM-CIA Nexus framework. So that's how long ago it's been. We talked about, my slides are kind of out of order here, I guess. We talked a little bit about modules. So there's different types of modules. For most people to be writing DRV modules, which are drivers. There's a bunch of others. This is not the complete list. MISC module would be the one that you would most likely see otherwise, unless you're dealing with streams. A MISC module is just a way to store a bunch of code in a library, so support routines. So the SCSI mid layer is actually MISC SCSI. Where do these things live? I talked about /kernel. Technically, /kernel is where you put things that you need in order to get to your root file system. And then there's platform kernel, and it actually would be platform i86 PC kernel. So there's a path component missing here. And that would be for things that, remember I talked about the implementation version, the implementation specific version of Intel, and then the generic Intel. This would be the implementation specific part of Intel. You almost never will be touching that, unless you're working on Zen. And then there's user kernel, which is where you put everything else. If you don't need it, in order to mount your root file system, put it in user kernel. The legacy here is to separate out, to have a small root file system, and you can have user be bigger and shared, like over an FS. But even though today you typically find that being done, it's still useful in order to keep the root archive, the boot archive, small. So, and I'm not going to talk about the boot archive any more than that. 32 and 64-bit. Remember, I talked about the fact that we can have both. An x86 box can be running a 64-bit kernel and can support both 64 and 32-bit kernels. So we have today, at least in illumos, I think SmartOS ditched the 32-bit support, didn't you?
We built it, but we only ship the 64-bit kernel, but we could ship the 32-bit.
Okay, so, and there's been some call to abandon 32-bit mode. We haven't made that decision yet. I suppose I'm one of the foot draggers here. So the way we take our modules, our 64-bit modules basically live in a subdirectory of the 32-bit directory with the AMD 64 name. For Spark, it's actually would be kernel DRV Spark v9. V9 is the 64-bit version of Spark. So module, what do you do about symbols? So most functions that are part of the DDI are in Unix or Gen Unix, which are basically the core kernel. And that's again split between the implementation specific and the non-implement, kind of the implementation generic piece. Those symbols everybody can see. If it's global in that in those modules, every driver in the system can see that. The linker just makes those available. But if you have a driver or a library, any other module, you will not see it unless you've established that you want to see it by when you build your module, you indicate a link dependency. So this LD minus N MISC SCSI, for example.